Yes, sir.
Yes.
Yes, sir.
So let's continue with our discussion. Now we are in the 20th lecture. So almost half course content we have covered. So some more discussion on PWM will happen based on other techniques which are related to high switching frequency. But where is the demarcation that we need to see? When do we need to have this low switching frequency kind of system? When do we need to have high switching frequency kind of system? This understanding is required. So we will try to cover that in this class. So we have seen various ways, like something is like called as selective harmonic elimination. Then instead of eliminating, you can go for optimized PWM technique. So these things we have seen in detail and how these are coming, in terms of simple case. If you try to see the two switching angle case, so here we have the contours plotted for different modulation index and then different harmonics going equal to 0. So these cases we can understand. And based on our requirement, let us say we want to reduce a particular harmonic, or we want to reduce set of harmonics, or the current total harmonic distortion, these things we can figure out. And then there could be another parameter such as torque, which is more relevant for motor. So instead of going for current harmonic or voltage harmonic, we can focus on torque harmonic. So we have understood how torque is generated in any machine, and particularly in context of induction motor, how is the harmonic torque coming up? What is happening when you apply some harmonic voltage on the motor, and how it is interacting with the fundamental components, and what is the impact of that on the total torque. So what we have understood is that in general, if you take, let's say, fifth and seventh, the most dominant harmonics, and basically the relative speed of these two harmonics with respect to fundamental is same. That's why we are considering these two harmonics over here. So when we take this, it interacts with, or both of this interact with the fundamental flux and fundamental current and result into a torque, which is something like this. So as you can see, the steady state torque, when we talk about, that means the DC torque, we see that all the quantities are constant over here. Say if you talk about flux, this means this is the RMS value. It's not about the sinusoidal component I'm talking about. It's the magnitude I'm talking about. So this is RMS value, say this is also RMS value. So this is all going to be a constant number. And then sine delta, where delta is also angle which is dependent on load, and most of the cases it is very, very close to 90 degree. So then in all such conditions, this is like a DC torque. So if I plot the torque of induction motor against time, not against omega, please note this. So if you try to plot the torque for the induction motor against time, it should be at a given load, it should be a fixed DC value. Now when you have the PWM voltage applied on the motor, you have harmonics, let us say V5 and V7 are the dominant harmonics. So what will happen? What will be the effect of that? The harmonic torque which we have generated because of these harmonic currents and the harmonic fluxes over there, this is creating something which is varying with time, even for a given load condition. And this variation is 6 times of the fundamental frequency. So how this will look like on the main torque? It will basically be a 6th harmonic waveform sitting on this DC component. So something like this is predominantly we are talking about 6th harmonic torque. So we say 6th harmonic because it is changing itself at 6 times the fundamental frequency. Now you will have obviously 12th harmonic also over there because you have V11 and V13 also present in the system. Similarly, you may have tau 18 because of V17 and V19 and so on. We may have many more torque harmonics. So when we are talking about a case where 6th harmonic is very, very dominant, then your torque waveform for induction motor may look like this. under the steady state condition. And under this condition, what you will see that because your torque is affecting your speed, no, you can subtract, let's say, tau v minus tau l. So the remaining portion, the ripple, this will have effect on speed, and speed will also be slightly varying. The magnitude may be lesser because there is some amount of filtering going on because of this first order response. Understanding my point? But still, you will see a similar kind of variation on speed as well. Correct? So this is what is expected when we have this kind of PWM voltage given over there. Just a second. Okay. So this completes our discussion. So whichever component, let's say, we are more bothered about, we can draw that, or no, have a condition where this will almost minimize that particular harmonic. So here this is on account of V5 and V7. Always see this point that any torque harmonic is because of pair of voltage harmonics. It's not because of one harmonic. So cases like when we are discussing selective harmonic elimination and we try to eliminate just one harmonic, say SHE-PWM, we are trying to eliminate V5 equal to 0 or V7 equal to just one harmonic. In these cases, actually the tau 6 may become very high because we have certain amount of balance also happening between these harmonics, V5 by 5 minus V7 by 7. Now that kind of thing is gone. So this balancing act which was there earlier, now one factor is gone. So the other may increase the sixth harmonic torque tremendously. So that is why this is one more disadvantage when we simply try to eliminate one harmonic. Sometimes we may encounter very high amount of harmonic torque coming up in the system. And that's the reason you are eliminating one, but you have not seen what the other is doing. The other one may be very high, and so the total effect on the sixth harmonic torque may be very high. Understanding my point? So this is another disadvantage when we have just blindly removing few harmonics. This may happen. Yes, of course, if we have, let us say, 3 switching angles in our system, in our quarter cycle, then say alpha 1, alpha 2, alpha 3. Now we have freedom. What we can do, we can maintain fundamental and we can eliminate V5 and V7 both equal to 0. This will certainly mean that our tau 6 is 0. Any other factor generating tau 6 is very small in magnitude. So the dominant component which is responsible for tau 6 is gone. So we can expect that tau 6 will be very, very close to 0. Only when you are eliminating both the harmonics which are responsible for generating the particular torque. You understand this point, this statement?
Yes, sir.
Good. So then we close the discussion on torque over here, and we will continue with more discussion on this kind of PWM technique. Okay, so now we have understood many different ways in which we can have our pulse width modulation designed and get the motor operated from that to have any parameter which you wish to make better, you can improve by that particular design. Now, there are a couple of fundamental questions which come whenever you are going with any PWM technique. See, you are going to operate a motor. Say this is the induction motor you have, and inverter is there. So there is some VDC voltage applied. Now, when we are operating any motor, the nameplate rating of the motors are fixed. Let us say line to line voltage is given, the frequency, fundamental frequency is given, rated slip may be given, No, rated torque may be given or power may be given. These things are given. Now, can we have any amount of DC bus voltage operating this motor? For example, I take 400 volts line to line motor, RMS value. Can I operate this motor with just 100 volts on the DC bus? Can I have this condition? Yes or no? Say something. See, PWM has never said that you maintain this amount of DC bus voltage, right? It did not say anything. It's only saying that you maintain certain switching angle and you will get whatever you want. But can we operate this motor with just 100 volts?
No, sir.
Or
No.
can we apply VDC equal to 1000 volts? Where shall we go?
Sir, it should be higher, like the VDC should be higher in such a way that
It should be higher than this.
yes, sir.
But should it, how much higher it should be? What is the limit? How
Like
do we quantify that?
Like based on the DC utilization, like DC bus utilization,
Yes,
we get
exactly.
the output should be maintained.
So we know that, let us say we take the simple case of two switching angle per quarter, say alpha 1, alpha 2. What voltage we are going to apply? We are going to apply say R phase voltage I am talking about, right? Fine, right? Now, what is the maximum value what I can achieve with this? What is the maximum value? Yes, say something. What is the maximum value what I can achieve?
2 VDC by pi.
2 VDC by pi, which is corresponding to the square wave operation, right?
Yes, sir.
Yes, sir.
Correct. This I am talking about a particular PWM where it can be classified as low switching frequency, which means we are discussing on basis of the switching angles within the PWM voltage. So maximum what may happen that alpha 1 may go equal to alpha 2 and then you will have a square wave operation which is giving the maximum voltage applied on the motor. So V1 max we can say is basically 2 VDC by pi. Understanding my point? So somewhere this maximum voltage is giving us the indication what my DC bus voltage should be. This maximum voltage is basically what? If 400 volts is your line to line voltage RMS value, then this should equate to this number. You understand my point? This is the peak value what I am going to get for the fundamental. This should match the peak value of the voltage which is getting applied on the motor or which is required by the motor. Understanding my point? So obviously we have a fixed definition for VDC. It cannot be random. So what we are basically having here is that VDC should be whatever this factor is coming. You can rework that and then pi by 2. So can you work out how much is, what is the number?
Sir, 515, sir.
515. What values you have put for root 2 and root 3?
Sir, I have put as root 3, sir. 513.01 is something.
Something around 512 point something volts is coming. It's okay. We don't mind having 510 volts. That is fine. But we cannot say that if this is the requirement, I will apply something like 800 volts on the DC bus. You understand my point? So in general, I have the relation between the VDC and line-to-line voltage like this. If my line-to-line voltage is given, I should have VDC which is close to this value. Now why? Why is that coming? We are trying to maintain V by F equal to constant. This V is dictated by the inverter. Modulation index into 2 VDC by pi. That's what it is. Now modulation index we are able to maintain on basis of alpha 1, alpha 2. But if you have too much of VDC, basically which means that you are going into overfluxing mode. You have too much flux over there in the machine. So motor may saturate if you have too much of DC bus voltage operating this particular machine. On the other hand, if you keep this VDC value too small, then flux may not be rated value. So this is something you are operating at lower flux value or under fluxing you are doing. So you are not utilizing the motor to its full potential. Which is why this number is important. You cannot have very large value of DC bus and we cannot have very less value of DC bus. You understand my point? So when we are operating with the PWM, we should know that what is the maximum amount of voltage that it can apply on this system. In this case, it is 2 VDC by pi. This I am talking about per phase peak value. This is the maximum value it can apply. So my DC bus voltage should be designed such that when I am reaching modulation index equal to 1, my voltage should be equal to the rated fundamental voltage of the machine. This is nameplate rating. The motor is telling what it should be when you are reaching modulation index 1. Understand my point? To avoid any of these situations, we should go with a proper design of this DC bus voltage. Am I clear?
Sir.
Any confusion in this? Yes or no? Quickly.
No, sir.
Okay, good. Now, the next question. The other thing which people might be interested in when you are operating with any PWM. First question, any general person who knows little bit of PWM, little bit of power electronics, they will ask, what is the switching frequency at which you are operating? Isn't it? That's a very common question. What is the switching frequency at which you are operating your motor? So people tend to relate the performance of the motor with the switching frequency. So they will have a very general understanding that yes, if switching frequency is large, that means performance is going to be good. If switching frequency is lower, performance is going to be inferior. Understanding my point? This is the common convention we all have. But when we are operating with a PWM which is of this nature, having let's say just one notch within pi by 2, how do we tell what is the switching frequency?
Number of time on and off.
Yes, that is the general definition of switching frequency, the number of on-off transitions. Just a second. Okay, so number of on-off transitions per second. That is what is the definition of switching frequency. On-off cycle, this is called the switching cycle. That means your device is, let's say, going off and then going on. or vice versa, on or off, and how many times that is happening per second, that gives the indication of switching frequency in general. Now here in such cases, when we have few notches over there or few transitions within the cycle, what we can do, we can count number of transitions. Let us say within 1 quarter cycle, how many transitions are there for this case?
2.
Again,
Two transitions are there.
1 on-off transition. I'm talking about the cycle, right?
Yes, sir.
So 1 on and off. This is 1 switching cycle. So if in 1 quarter we have 1 switching transition or 1 switching cycle, then how many we will have in the entire cycle?
Two times.
In the entire fundamental frequency or fundamental line cycle. So 4 quarters are there, and so we will have 4 on-off transitions or 4 switching cycle. Correct? Fine or not? Speak up,
Yes,
speak
sir.
up. But something we have missed out. We do have transitions happening at 0 and pi as well. So 0 and 2 pi may be same, but at least 0 and pi are not the same transition which is happening. So one inevitable transition we have at 0 and pi, one pair of switching transition. So which means we have 4 plus 1 in the entire fundamental cycle. So what we can say, the total number of transitions are 4 plus 1. Correct? If I define this quantity by, let's say, a number p, so we will have better definition of this. So this p is basically number of on-off cycles within a fundamental cycle. You are understanding the definition here? So this is basically 5 in case of 2 switching angles per quarter. This number you can call as pulse number. Correct? So now, when we say that there are 5 switching cycles in one fundamental cycle, then can I not say that my switching frequency is p times of the fundamental frequency? Understanding my point?
Yes.
So this is the parameter, this pulse number, which is defining the quality of waveform in general. Let us say if someone says that, okay, my switching frequency is 10,000, or okay, say 10 kilohertz. Generally, what understanding you will have about the system? What understanding you will have? Say something like it would be a good performance or bad performance, what you will have?
Sir, it depends on the application.
Okay, let us say motor application.
Higher the switching frequency, better will be the performance, but at the same time your losses and
Forget
will
about
be-
losses. I have very good mechanism to take out all the losses, and I can
performance
manage
will
my
increase.
temperature very well. So generally what you will have as when you hear this kind of switching frequency, what understanding you will get?
So number of cycle is 10 in the fundamental.
Okay, I be more specific. What feeling you will have about the quality of the line current waveform?
It will be having lower THD.
Lower TH, that means a good quality you are expecting, right?
Yes,
When
sir.
I say 10 kilohertz of switching frequency. Fine, right? Yes or no?
Yes, sir.
Okay, now Have I said anything about my fundamental frequency so far in this?
No.
Now let us say if I add my fundamental frequency is 2 kilohertz. Now what understanding do you get from here?
Performance may not be that good. We were expecting is 50 hertz.
You understand my point? So switching frequency alone is not the parameter which decides the quality of the waveform. It is with respect to the fundamental frequency that decides what quality we are going to get. Although we have 10 kilohertz of switching frequency, but my fundamental frequency itself is 2 kilohertz. In effect, what I am having pulse number of how much? How much is the pulse number here now?
5.
5. And which is basically this kind of waveform what I have drawn here. You understand the point? So this pulse number actually gives a better understanding how your system is going to perform in terms of, let's say, quality of line current and other things, rather than just the switching frequency. So you also need to know when someone says, yes, I have 5 kilohertz switching frequency, but you need to ask what is your fundamental frequency. Then you can say, yes, if the pulse number, let us say in general, you can have this understanding. If pulse number is going beyond, say, 21, you can say that, yes, the performance could be good. By saying pulse number, you have also included the fundamental frequency in that. You understand my point? Now, if I say that my pulse number is 5, someone is saying that I am operating with a PWM which is having P equal to 5. So if that person is operating a fundamental of 10 Hertz, the switching frequency is going to be how much? What will be the switching frequency? 50 Hertz. Now the same fundamental frequency becomes 50 Hertz. How much switching frequency that person will have?
250.
250 Hertz. So this variable nature of frequency is automatically coming with the fundamental frequency, which means the nature of PWM is not changing. For this entire operation 10 Hertz to 50 Hertz, he is having a waveform, output waveform, which may look like this. One notch in 1 quarter cycle, and then so this is going to be the nature of PWM for the entire operation, which means more or less we have decided that what quality we are going to get from the system, irrespective of the fundamental frequency and switching frequency here, because we have fixed the pulse number. So that is how this is a generic term which can tell a lot of things about the property of how your waveform or the quality of the output current, how it's going to be. You understand my point?
Yes, sir.
Yes, sir.
Yes, sir.
Correct. Now, let us say this is only for 2 switching angle I have said. Let's say I have n number of switching angles over here. So in general, the pulse number can be said as 2n plus 1. So 1 corresponds to the transition at 0 and pi, and this 2n is basically n amount of switching angles which are coming within the quarter cycle. In general, for such system or any system, if you can define the number of switching angles within the quarter cycle, this is going to be the pulse number. You understand the point? So when I say 2n plus 1, there is some very important thing to notice, that this pulse number is only going to be odd. Let us say starting from 3, 5, 7, then 9, 11, 13, 15, etc. It cannot be even. Correct? It could be 1 also. 1 corresponds to the 50 Hertz of switching frequency. if you have 50 hertz of fundamental frequency. That means the square wave operation. And as you keep increasing the number of switching angles within the quarter cycle, this pulse number will keep increasing. Correct? Yes or no?
Yes, sir.
So by having this kind of pulse number, we are inherently ensuring full wave symmetry as well as half wave symmetry. The other things, quarter wave symmetry and three phase symmetry, is up to the designer how they want to have the angles within the cycle. But these two things ensure that you will not have any subharmonic and any even harmonic in the system. You understand the point?
Yes, sir.
You can try, out of your interest, you can try drawing a waveform with pulse number 6. So you will understand what is missing where. Okay. Now, let us understand a little bit more about where do we need to apply this kind of PWM, where do we need to apply something else. Now, this is very much related to the dynamic transition or characteristic of the device, say IGBT or diode, anything you can take, all will have similar. So the dynamic characteristic decides what we should have and what we should know apply on the system, whether we should have this kind of PWM or something simpler like sine triangle. So generally what we expect from the ideal switch, that we have this kind of switch. When it is open, there is no current flowing through this, and when it is closed, there is no voltage drop across the switch. And any amount of current can flow. Here any amount of voltage can be blocked. This is steady state characteristic we are having. Now, how does the transition happen from one state to another state and vice versa? Is it instantaneous or there is some delay? This kind of question we need to have here. So let's say when we talk about a leg, something like this. And say some inductive load is connected over here. So which is what we are operating. This is voltage source, so this has to be current source. So some inductive load is getting operated, or it could be resistive load simply. Now, practically we know that definitely it's not going to be instantaneous. So if ideal device we talk about, it is off, that means voltage is high, and when the gate pulse is applied, it will immediately go to zero value of voltage across the device. And current, on the other hand, which will be zero up to this point, will suddenly rise and start at the maximum value. That will be the ideal characteristic. But we know that definitely that's not going to happen. Correct? There is certainly going to be a delay. So what may happen that if this device is operating, let's say this is on, and you try to turn it off, and this device which was off, you are trying to make it on, there may be some delay, which means what is expected that while one device is turning off, the other may also get turned on. So there could be a possibility of short circuit or shoot through across the DC bus. Both devices may get turned on together. Understanding my point? Because of the delay, every process is delayed. From on to off, there is a delay, and from off to on, there is a delay. So there may be some overlap period where these both may be in between some state, or both may be on. That is the worst condition what may happen. To avoid this, what we do, we introduce some kind of delay before turning on the other switch. Let us say, now a little bit of converter we are trying to understand over here. Let's say this is the pulse given for the top device. Gate pulse for top device. Now what is expected in general that your bottom is exactly inverted, is not of this top. Correct? Now, this is the condition which I am talking about. Here, the device is going off and the other device is getting turned on. Now, this is where the possibility of shoot through may be there. Shoot through the DC bus, which is what we are trying to avoid. So what we do, we introduce something called as dead time or blanking time. For the incoming pulse. This is only done for the incoming pulse. We do not disturb the outgoing pulse, which means that we will not touch this edge, but we will modify this. Similarly, here we will not disturb this. This is okay, but we will modify this. Then again, we will not disturb this. This is fine. We will modify this. So what we will do, we will delay the incoming pulse by a certain time, let's say TD, which actually depends on the device, how fast it is turning on. So we can have lower value of TD. So what will happen in effect, our top device will have gate pulse which will be looking like this. Notice the delay from the actual rising edge. You understand the point? And for the bottom, so this I call as GT prime, let us say, and GB prime would be delayed, and then it will continue up to the full time period, up to the turn off time, and then this also will travel up to this point. So there is certain gap between the falling edge and the rising edge of the next pulse. This delay I am talking about, which is called as blanking time or dead time. This we are giving intentionally. This is nothing to do with how device is responding. This we are keeping intentionally. We are creating this dead time in our system. So this gate pulse is applied only after certain delay. Understand the point? Now, this dead time could be something of the order of few microseconds. Reasonable dead time could be a few microseconds. Sometimes it is 2 microseconds, 4 microseconds, or for bigger devices, when we have high power devices, then it may be even 10 or 20 microseconds, which is a big number. So we have the TD number dependent on the device. We will see in a short while how this is for a bigger device, high power device. Now, when we are having this kind of gate applied for our system, obviously we have, let's say, this leg with anti-parallel diodes. Connected over there, and we have a situation where this device is off. Let us say top device is off, and the bottom device is still not turned on. So this is also off. Understanding my point? There is a delay between the two. This device is turned off first, and then this device is getting turned on. And here we have inductive load, so current cannot be discontinuous. So who will support the current during this time, during the blanking time? Both the devices are off. It cannot conduct during the off state. So which device will support here, or which component will support here?
The diodes.
Anti-parallel diode.
So if the current is going out from the converter, then this bottom diode will come into picture. And it will take over the complete current. And if the current is coming inside the converter, then this top diode will take over this during the dead time when both the devices are off. Which means whenever we are going to turn on or turn off any device, let us say if I talk about the top device, we are going to turn on or turn off, it is always going to have a transition with a diode. See, when this is going to turn off, this is conducting. So transition is from device to diode, current transition. Understand the point? Vice versa, when we have this device on and we are taking it off, then also the current will shift from device to diode. So in case of voltage source converter, the current transition is always from device, let's say IGBT, to diode, or vice versa. It is never between two devices directly. It will not happen that this is conducting and then this is getting transferred to this directly. You understand my point? So you are taking from, let's say, device, giving it to diode. Then based on the direction, if required, when this device is on, it will take over that. Understanding my point?
Yes, sir.
So this you need to remember. The transition of current is always between the device and diode. And it is opposite diode, of course. This device and this diode. Correct? So because of this, what is going to happen is that our dynamic characteristic of device is not just dependent on what it is, but it is dependent on the circuit conditions. And let's say we are talking about highly inductive load or some current source kind of condition. Now we will take this circuit as our reference and we will try to plot the dynamic response or dynamic characteristic of the device, IGBT, let us say. So say this device is off this condition and you are going to turn it on. So when the device is off, your voltage is going to be full. Full voltage is applied across this VDC. And what is the voltage across the diode? Say nearly 0. That is how the KVL will be also satisfied. VDC is here and your VDC is getting dropped here. Now, say at this moment you have applied the gate pulse. So what will happen? As you apply the gate pulse, there may be certain delay before the device will react to that. And then the VC voltage will start dropping. It cannot suddenly go off. So it will drop slowly and it will go to very close to 0. What will happen to the current?
It will rise from 0 to 500.
It will rise, there is no doubt. But how?
Sir, depending on the load.
We have set the load. So now understand what is happening. Just let us try to see from the circuit point of view again. What we have a device. I will not draw the antiparallel diode for this because that's not conducting, and the device on the bottom side because that is also not conducting. This is the scenario. You have VDC voltage coming across this initially and V equal to 0 coming over here. Diode. The moment this is dropping slightly, what will happen? The device voltage will become VDC minus delta V and the diode voltage will become delta V. You understand the point? The moment this has dropped by amount delta V, this will become delta V because it has to satisfy the KVL. Total voltage across this must be VDC. Now, diode cannot have a situation where current is flowing through that and there is some voltage also across it. That is diode property. Whenever there is current through the diode, immediately the voltage will go to 0. Now what we are forcing some voltage across it. And of course, the polarity is opposite. So immediately the current will get transferred to the device. I am talking about this direction of current. So instead of going from this, it will start flowing through this. So here what we will see, that there will be a sudden jump in current. So, okay, I'll draw in blue color. Sudden, almost steep rise in current, and it will start flowing through the device. And the voltage will keep falling in its natural way. You understand this point? Yes or no?
Yes, sir.
So this is how the device current is going to behave. There will be one more interesting thing which will happen on this current, because this is diode. So diode current will fall almost instantly, and there is something known as reverse recovery current also associated with diode. We all know what it is. But the effect of this reverse recovery current will be, because total current is same, it is I. So whatever is going negative, that will appear on the device, and there will be a overshoot on the device current. Now this is strange. Generally we have seen overshoot on the voltage, but this is something like overshoot on the current. This happens because of the reverse recovery, what is happening in the diode. This is the turn on characteristic. You understand my point? Now, let us go the other way, or shall we complete it here? Okay, so let us see a characteristic which is captured in lab actually. So how that is. This is a practical characteristic which is captured in lab. Let us see how that is. And this is for a device which is high power device. Correct? Are you able to see this? I may not be able to annotate many things on this. So this is how my device voltage is. It is high, the device is off, and I am applying my gate pulse over here. The S is the gate pulse applied. There is certain amount of delay, only after which my actual gate voltage has started changing. You see this delay? This is what I was talking about, the initial delay. Not that time, delay, which is happening because you apply the pulse and device reacts on that. There is a delay in that. Then the gate voltage has stabilized almost. So the moment it stabilizes, this starts falling. And you see the plateau over here. This is where the device current starts changing suddenly and it becomes maximum. This is the kind of overshoot I'm talking about on the current. This is happening on account of reverse recovery. Understanding my point? Sometimes this plateau is also called as the plateau on VC is also called as Miller plateau. So this is where the current actually starts changing. And it reaches the maximum, and this is the rated value actually you see here. So the reverse recovery is dropping and then going to the actual value of what is there in the circuit. And then the VC has also dropped and come back to 0. So here is the 0 for VC. So it is dropping down and then coming to 0. So these are important instances where the current is changing, where the device voltage is changing. This is how it is. Now, what is the effect of this? That during this transition, we have non-zero voltage and non-zero current both. Generally for device, what we see that whenever voltage is high, current is very low, or whenever current is high, voltage is low. That is the on and off situations. But during this transition, we have both the voltage and current significantly high. The result is energy loss in the device, which is known as switching energy loss. And particularly because this is happening during the turn on, so this is turn on switching energy loss. So this red waveform is basically indicating, see here it is 0, here also it is almost 0. In between, this is coming as some curve, which is very high. The value is high. So we have switching energy loss associated with the turn on of the device. Understand the point? So remember these instances. Now you see the time period. This each division is like 0.8 seconds. So it is almost taking 2 seconds, sorry, microsecond. It's almost taking 2 microsecond to drop from this value to this value. Almost. So 3 blocks almost, so 2.4 you can say. This is a device which is like rated at some 4500 volts and 1200 amps IGBT by Infineon. And this is the kind of delay we are expecting in turn on alone. Turn off we have not seen so far. You understand the point? So which is why we need dead time over there so that it can manage all these transitions easily. Fine?
Yes, sir.
Any confusion in this? Okay. Now, just a glimpse of what will happen during turn off, and we will discuss a little bit more tomorrow. I thought I'll be able to complete, but these discussions are important. I cannot rush through all this. Now the scenario is that we are talking everything in terms of the top device. Same discussion can be extended for bottom device as well. Now the scenario is that this device is on, correct? There is current flowing through this and the voltage is blocked by the diode. So what we have basically, if we draw the dynamic characteristic of device, we have current at some high value and voltage is very small, say voltage is in black color, it is a small, and at this instant we apply the gate pulse. We have removed the gate pulse. That is better way to say. At this point, we have removed the gate pulse, which means the device is bound to come out of the conduction mode. It is going to go into the blocking mode, but how that will happen? That is what we have to see here. So maybe one more minute, I will continue the discussion and then I will continue tomorrow. Fine. So what will happen? Now how the voltage and current will respond? Obviously, the current is going to fall slowly. And there will be, here also there may be some kind of plateau and then there will be a long tail current. These are all characteristics of IGBT, how it happens, how the fall in current happens. But how about the voltage? Now again, we know that in every situation KVL, KCL are going to be satisfied. So here, if current I was flowing here, that was going out, the moment we have removed the gate pulse, this will reduce by, let's say, some delta I. Now where that delta is going to come from? It is going to come from the diode. This will start conducting the remaining delta I. And again, the condition what we said just a minute back, if there is current flowing through the diode, there cannot be any voltage across this. So this voltage drops to 0 suddenly, and so this voltage VCE suddenly comes to VDC almost instantly. You understand my point? This is on account of circuit what we have over here. Okay, so more discussion tomorrow. During the lab, we will discuss the lab assignment, whatever difficulties you are having, but try to complete by tomorrow now.